What if I told you that for every atom in your body, there exists a perfect mirror image somewhere in the universe? An identical twin made of the same stuff, but with one crucial difference that makes it the most dangerous substance known to science. This isn't science fiction. This is antimatter, and it's been hiding in plain sight since the very beginning of time. Now, before we dive into this rabbit hole together, I need to ask you something. Have you ever wondered why you exist at all? I mean, really thought about it? Because according to the laws of physics, you shouldn't be here. None of us should. The universe should be empty, cold, and completely lifeless. The fact that you're watching this right now is actually one of the greatest mysteries in all of science. My name is Alex, and I've spent the last 3 years diving deep into the most mind-bending concepts in physics, and antimatter might just be the strangest one yet. In this video, I'm going to reveal why antimatter is called the mirror of reality, why a single gram of it could power your house for decades, and most importantly, why the existence of antimatter threatens everything we think we know about the universe itself. But here's where it gets really wild. I've discovered something that most people don't realize about antimatter. It's not just some exotic substance locked away in particle accelerators. It's being created right now, above your head, in the atmosphere. It's being produced inside your own body at this very moment. And somewhere out there in the cosmos, there might be entire galaxies made of the stuff, invisible to our telescopes, but very, very real. What I'm about to show you will completely change how you see reality. Because antimatter isn't just the opposite of matter, it's the key to understanding why anything exists at all. And by the end of this journey, you'll understand why some scientists believe that antimatter might be the most important discovery in human history. So let's start with something that sounds simple but will blow your mind once you really think about it. Imagine you're looking in a mirror. You see yourself, but everything is reversed. Your right hand appears to be your left hand. Any writing on your shirt is backwards. It's still you, but it's you flipped in a very specific way. Now, what if I told you that every single particle in the universe has a mirror image just like this? Not just similar, but absolutely identical in every way, except for one fundamental property. This is the basic idea behind antimatter. For every electron, there's an anti-electron called a positron. For every proton, there's an antiproton. For every neutron, an antineutron. These antiparticles have exactly the same mass as their normal matter counterparts, exactly the same size, exactly the same behavior, but their electric charge is flipped. Where an electron has a negative charge, a positron has a positive charge. Where a proton is positive, an antiproton is negative. It sounds almost trivial, doesn't it? Just flip a sign here and there, and you've got antimatter. But this tiny difference creates the most explosive reaction possible in our universe. When matter and antimatter meet, they don't just react like hydrogen and oxygen making water. They don't combine like sodium and chlorine making salt. They completely annihilate each other, converting their entire mass directly into pure energy, according to Einstein's famous equation E=mc². Let me put this in perspective for you. When you burn gasoline in your car, you're converting about 1/billionth of its mass into energy. Nuclear fusion, the process that powers the sun, converts about 0.7% of mass into energy. But when matter and antimatter annihilate, 100% of their mass becomes energy. 100%. It's the most efficient reaction possible in the universe. A single gram of antimatter annihilating with a gram of matter would release as much energy as the bomb dropped on Hiroshima. Just 2 grams of material, and you've got the power of a nuclear weapon. Scale that up to a kilogram, and you're talking about energy equivalent to 43 megatons of TNT. That's more than the largest nuclear bomb ever detonated. But here's what really gets me. This isn't just some theoretical calculation. This actually happens. Right now, in particle accelerators around the world, scientists are creating tiny amounts of antimatter and watching it annihilate with regular matter. We've seen this reaction, we've measured it, we've harnessed it, and it works exactly as the equations predict. Now you might be thinking, okay, that's cool, but where does antimatter come from? How do we make it? And that's where the story gets really interesting, because antimatter isn't just something we create in labs. It's everywhere. Every second, cosmic rays from deep space are slamming into our atmosphere at nearly the speed of light. These high-energy particles collide with atoms in the air, and in those violent collisions, pairs of particles are born, matter and antimatter, created together in equal amounts. Right now, above your head, positrons are being created and immediately annihilating with electrons in the atmosphere. It's happening constantly. A invisible fireworks show powered by the universe itself. But it gets even stranger. Your own body is creating antimatter. Certain radioactive elements naturally decay by emitting positrons. Potassium-40, which exists in every banana you've ever eaten, occasionally spits out a positron. Carbon-11, which is used in medical imaging, is a positron emitter. There are people walking around with radioactive traces in their bodies right now, glowing with antimatter reactions. And then there are the truly mind-blowing sources. Lightning creates antimatter. When those massive electrical discharges tear through the atmosphere, they create conditions so extreme that matter and antimatter pairs pop into existence. Some scientists think that every lightning bolt on Earth is accompanied by a brief flash of antimatter annihilation. But perhaps the most incredible source of all is black holes. Stephen Hawking predicted that black holes should emit radiation as they evaporate, and part of that radiation should be antimatter. We're talking about objects so massive that they bend space-time itself, and they're spewing out the mirror image of reality. Now, here's where we run into the biggest mystery in all of physics. If matter and antimatter are created together in equal amounts, if the universe started with a perfect balance of both, then where did all the antimatter go? This is called the matter-antimatter asymmetry problem, and it's one of the deepest puzzles in science. In the early universe, just after the Big Bang, matter and antimatter should have been created in exactly equal quantities. They should have immediately annihilated each other, leaving behind nothing but pure energy. The universe should be empty. No stars, no planets, no galaxies, no you. But obviously, that's not what happened. Somehow, somewhere in those first few moments after the Big Bang, the universe cheated. For every billion pairs of matter and antimatter particles that annihilated each other, there was one extra matter particle left behind. Just one in a billion. That tiny imbalance, that minuscule asymmetry is the reason everything exists. Think about that for a moment. You, me, every star in the sky, every planet we've ever discovered, every atom in every living thing, we're all made from the leftover scraps of a cosmic annihilation event. We exist because the universe somehow managed to save a fraction of a percent of matter from total destruction. But what caused this imbalance? Why did matter win out over antimatter? This is where things get really speculative, really exciting, and really weird. Some physicists think the answer lies in something called CP violation. That's a fancy way of saying that the laws of physics might not be perfectly symmetric. Maybe, under certain extreme conditions, matter and antimatter don't behave exactly the same way. Maybe there's a subtle preference built into the fabric of reality itself. Others think the answer might involve extra dimensions. What if our three-dimensional universe is just a slice of a much larger, higher dimensional space? What if antimatter doesn't disappear, but instead gets banished to a parallel reality that we can't see or touch? And then there are the really wild ideas. What if time itself played a role? What if the universe went through a period where time flowed differently, where cause and effect worked in reverse, where the normal rules of physics were suspended long enough for matter to gain the upper hand? But here's what really keeps me up at night thinking about this. What if the antimatter didn't disappear? What if it's still out there? Imagine for a moment that somewhere in the vast cosmos, there are entire galaxies made of antimatter, stars burning antifuel, planets orbiting antistars, maybe even life forms made entirely of antiparticles. From a distance, these antimatter galaxies would look identical to normal matter galaxies. Light is its own antiparticle, so photons from an antimatter star would be indistinguishable from photons from a regular star. The only way we'd know is if matter from our galaxy somehow encountered antimatter from one of these hypothetical anti-galaxies. And when that happened, the result would be the most spectacular explosion in the history of the universe. We're talking about gamma rays, so intense they could sterilize entire solar systems, energy releases that would make supernovas look like birthday candles. Some astronomers are actually looking for evidence of this. They're scanning the sky for the telltale signature of matter-antimatter annihilation on a cosmic scale. So far, they haven't found anything definitive, but the search continues because if antimatter galaxies do exist, they would revolutionize our understanding of the universe. Now, you might be wondering, if antimatter is so dangerous, so explosive, how do scientists work with it? How do you store something that annihilates the moment it touches any normal matter? The answer is both elegant and incredibly complex. You use magnetic fields. Since antimatter particles are electrically charged, they can be trapped and held in place by carefully designed magnetic bottles. Imagine invisible magnetic walls that keep the antimatter suspended in a perfect vacuum, never touching the sides of its container. The largest antimatter trap in the world can hold about 10 million antiprotons. That sounds like a lot until you realize that 10 million antiprotons have a mass of about 16 femtograms. A femtogram is 1/4,000,000th of a gram. To put that in perspective, the period at the end of this sentence contains about 50 billion times more matter than the world's largest antimatter trap. Creating antimatter is also incredibly expensive and inefficient. It costs about $25 billion to make a single gram of positrons. That makes antimatter the most expensive substance on Earth by a factor of about 1 trillion. Even gold, at current prices, would cost less than 1,000th of 1 cent per gram compared to antimatter. And the energy efficiency is terrible. For every unit of energy you put into creating antimatter, you get back maybe 1/10000000th of that energy when it annihilates. It's like paying $1 million for a battery that stores $1 worth of electricity. But despite these limitations, scientists continue to study antimatter because it might hold the key to understanding the deepest mysteries of existence. Why do we have something instead of nothing? What happened in those first moments after the Big Bang? Are there hidden symmetries in nature that we haven't discovered yet? Some researchers are even exploring practical applications. Could we use antimatter as fuel for spacecraft? A few grams of antimatter could theoretically propel a spaceship to nearby stars in just a few decades. Could we use it for medical treatments? Antimatter particles can be precisely targeted to destroy cancer cells without damaging healthy tissue. But all of these applications are still decades or centuries away. For now, antimatter remains one of the most mysterious and fascinating subjects in all of science. And this brings us to something that absolutely blew my mind when I first learned about it. Remember how I said antimatter is like looking in a mirror? Well, it turns out that analogy goes way deeper than just flipped electric charges. The relationship between matter and antimatter reveals something profound about the very structure of reality itself. See, in physics, we have this concept called symmetry. And symmetry isn't just about things looking pretty or balanced. It's about the fundamental laws that govern how the universe works. When physicists talk about symmetry, they're talking about operations you can perform on a system that leave it unchanged. Rotate a perfect sphere, and it looks exactly the same. Reflect a snowflake, and you get an identical pattern. But here's where antimatter gets really weird. It's connected to 3 different types of symmetry that, when combined, seem to be perfectly preserved in nature. These are called C, P, and T symmetries. C stands for charge conjugation, which is basically swapping particles for antiparticles. P stands for parity, which is like looking in a mirror, flipping left and right. And T stands for time reversal, running the clock backwards. Now, individually, these symmetries can be broken. Nature does seem to have a slight preference for leftover right in certain situations. Some particles decay in ways that violate parity. And we already talked about how charge symmetry is broken, since we have more matter than antimatter. But here's the incredible part. When you combine all three operations together, CPT symmetry appears to be perfectly preserved, always. What this means is that if you take any physical process, swap all the particles for antiparticles, flip it in a mirror, and run it backwards in time, you get a process that's just as valid as the original. It's like the universe has this deeper level of symmetry that remains unbroken no matter what we throw at it. But think about what this implies. If CPT symmetry is truly fundamental, then somewhere in the mathematical structure of reality, matter and antimatter are just different perspectives on the same underlying truth. They're not separate things. They're different faces of a single deeper reality that we can only see pieces of at a time. This gets even stranger when you consider what happens at the quantum level. In quantum field theory, which is our best description of how particles behave, every particle is really just an excitation in an underlying field that fills all of space. The electron field, the proton field, the photon field. These fields are like invisible oceans, and particles are like waves on the surface. But here's the kicker. Antimatter particles aren't separate excitations in separate fields. They're the same fields, just vibrating in the opposite direction. It's like the difference between a wave moving left and a wave moving right on the same string. Same string, same physics, just pointing different ways. And this leads to one of the most mind-bending ideas in all of physics. What if antiparticles aren't really separate entities at all? What if they're just regular particles moving backwards through time? I know that sounds insane, but hear me out. This idea was proposed by physicist John Wheeler and his student Richard Feynman back in the 1942. They suggested that a positron, an anti-electron, is actually just an electron that's moving backwards through time. When you see matter and antimatter annihilate, you're not seeing two particles destroy each other. You're seeing one particle change direction in time. Picture this. An electron is moving forward through time, minding its own business. Then something happens, some interaction, that causes it to reverse direction and start moving backwards through time. To us, watching from our forward-moving perspective, this backwards-moving electron looks like a positron. It has the opposite charge because we're seeing everything in reverse. Now, I'm not saying this is definitely how antimatter works. There are problems with this interpretation, and most physicists today think of antiparticles as genuinely separate entities. But the fact that this idea even makes mathematical sense tells you something profound about the nature of time and reality. And speaking of time, here's something that'll really mess with your head. In our everyday experience, time has a direction. We remember the past, we don't remember the future. Eggs break, they don't unbreak. Hot coffee cools down, it doesn't spontaneously heat up. But at the fundamental level, at the level of individual particles, time doesn't seem to have a preferred direction at all. If you filmed an electron bouncing around in empty space and played the video backwards, you couldn't tell the difference. The laws of physics work exactly the same way forwards and backwards. It's only when you get to large collections of particles, when statistical effects start to dominate, that time develops an arrow. This is deeply connected to the antimatter mystery. If the fundamental laws of physics are perfectly time-symmetric, then the Big Bang should have created equal amounts of matter and antimatter. The fact that it didn't means that something broke time symmetry in those first moments after the universe began, something that we still don't understand. But here's where things get really speculative, really exciting. What if the solution to the antimatter puzzle isn't that antimatter disappeared? What if it's that antimatter is still here, but we're looking for it in the wrong place? Some theories suggest that our universe might be just one of many, not just other galaxies or other regions of space, but entirely separate universes with their own laws of physics, their own space and time. In some of these theories, called multiverse theories, our universe and a mirror antimatter universe could have been created together at the Big Bang, like cosmic twins. In this antimatter universe, everything would be made of antiparticles, anti-atoms forming anti-molecules, forming anti-planets orbiting anti-stars. And if there were life in such a universe, it would be anti-life, made of antiparticles, but following the same chemical and biological processes we see in our own universe. From their perspective, we would be the antimatter universe. They would think of themselves as being made of normal matter, and they would wonder where all their antimatter went. It's a perfect symmetry, a cosmic mirror that solves the asymmetry problem by simply putting the missing antimatter somewhere we can't see it. Now, I want to be clear, this is highly speculative. We have no direct evidence for antimatter universes or multiverses of any kind. But the math works out, and it's a beautiful solution to one of physics' biggest puzzles. And there's another possibility that's even stranger. What if antimatter isn't missing at all? What if it's hiding in plain sight, and we just don't know how to see it? This idea comes from some cutting-edge theories about the nature of gravity in space-time. We know that antimatter has positive mass, just like regular matter. But what we don't know for certain is exactly how antimatter behaves in a gravitational field. Now, almost everyone expects that antimatter should fall down just like regular matter. Drop an anti-apple, and it should fall toward the Earth, not away from it. But here's the thing. We've never actually tested this. We've never dropped antimatter in Earth's gravity to see what happens. The reason is simple. We can barely make any antimatter at all, and what little we can make is stored in magnetic traps in perfect vacuums. You can't exactly take it outside and drop it. But several experiments are being planned to test this, and the results could be revolutionary. What if antimatter falls up instead of down? What if it has some kind of repulsive gravitational effect? This would explain why we don't see antimatter in the universe. It's not that it was destroyed or banished to another dimension. It's that it was gravitationally expelled from matter-rich regions like galaxies and solar systems. In this scenario, there could be vast clouds of antimatter floating in the empty spaces between galaxies, invisible to our telescopes because there's no regular matter nearby for it to annihilate with. It would be dark matter, but not the kind of dark matter we usually talk about. It would be dark because it doesn't interact with light in ways we can detect, but it would still be made of familiar particles, just antiparticles. This is still extremely speculative, and most physicists expect that antimatter will behave just like regular matter in a gravitational field. But until we test it, we won't know for sure. And that's what I love about science. There are still fundamental questions about reality that we haven't answered yet. But let's get back to something we can test, something we can measure, the practical applications of antimatter. Because despite all the theoretical mysteries and speculative ideas, antimatter is real. We can make it, we can store it, and we can use it. The most immediate application is in medicine. Right now, doctors use a technique called positron emission tomography, or PET scans, to look inside your body. They inject you with a radioactive tracer that emits positrons. When those positrons encounter electrons in your body, they annihilate and produce gamma rays. By detecting those gamma rays, doctors can create detailed images of your organs and tissues. This isn't science fiction. This is happening in hospitals around the world every day. Antimatter is being used to diagnose cancer, heart disease, and neurological disorders. It's saving lives right now. But the potential goes far beyond medical imaging. Researchers are exploring whether beams of antiprotons could be used to treat cancer more precisely than current radiation therapy. The idea is that antiprotons could be targeted directly at tumor cells, where they would annihilate and release their energy exactly where it's needed, without damaging healthy tissue. And then there's space travel. This is where antimatter gets really exciting from a practical standpoint. Chemical rockets, the kind we use to get to the Moon and Mars, are incredibly inefficient. They can only achieve a small fraction of the speed of light, which means that trips to even the nearest stars would take thousands of years. Nuclear rockets are better, but they're still limited by the amount of energy you can extract from nuclear reactions. But antimatter rockets could, in principle, achieve significant fractions of the speed of light. We're talking about trips to nearby stars in decades instead of millennia. The numbers are staggering. A spacecraft powered by matter-antimatter annihilation could theoretically reach about 10% of the speed of light. At that speed, you could reach Proxima Centauri, the nearest star, in about 40 years. Alpha Centauri would be a 43-year journey. Suddenly, interstellar travel goes from impossible to merely extremely challenging. But here's the catch. Remember those cost figures I mentioned earlier? $25 billion per gram of antimatter? To fuel a spacecraft to the nearest star, you'd need maybe 100 grams of antimatter. That's $2.5 trillion just for the fuel. And that's assuming we could make antimatter 1,000,000 times more efficiently than we can today. So we're not booking tickets to Alpha Centauri anytime soon. But the potential is there. And as our technology improves, as we learn more about antimatter production and storage, these dreams might become reality. There's also the possibility of using antimatter for power generation here on Earth. A few grams of antimatter could power a city for years. No carbon emissions, no nuclear waste, just pure energy from the most efficient reaction in the universe. But again, the practical challenges are enormous. Not just the cost and difficulty of production, but the safety issues. How do you safely transport and store a substance that could level a city block if containment fails? How do you prevent it from being weaponized? These are problems that don't have easy solutions. Yet despite all these challenges, research continues. Because antimatter represents something more than just another energy source or propulsion system. It represents our quest to understand the deepest mysteries of existence. Why is there something rather than nothing? What happened in those first moments after the Big Bang? Are there hidden symmetries and structures in reality that we haven't discovered yet? Every time we create an antiproton in a particle accelerator, every time we trap a positron in a magnetic field, we're probing these fundamental questions. We're looking into the mirror of reality and asking what it can teach us about ourselves and our universe. And there's something deeply moving about that. Here we are, collections of atoms that somehow became conscious, using our intelligence to create and study the mirror image of our own substance. We're matter studying antimatter. We're the universe investigating its own reflection. In the next part of our journey, we're going to dive even deeper into these mysteries. We're going to explore what happens when you try to make antimatter atoms, not just individual antiparticles. We're going to look at the most ambitious experiments ever conceived, projects that are trying to answer whether antimatter falls up or down, whether anti-atoms can form anti-molecules, and whether there might be entire antimatter solar systems hiding in the dark spaces between stars. Because the story of antimatter isn't just about physics, it's about the nature of existence itself, and we're just getting started. But before we dive into those incredible experiments, I need to tell you about something that happened in 1995 that changed everything. For the first time in human history, scientists at CERN didn't just create individual antiparticles, they created actual anti-atoms, complete, stable structures made entirely of antimatter. Think about what this means for a second. An atom is a complex system. You've got a nucleus made of protons and neutrons, surrounded by electrons in specific energy levels. The whole thing is held together by electromagnetic forces, following the rules of quantum mechanics. It's like a tiny solar system, except instead of gravity, it's electric charges keeping everything in orbit. Now imagine building that same structure, but with antiparticles. Antiprotons and antineutrons forming an antinucleus, with positrons orbiting around it. Every charge is flipped, but the structure remains identical. It's like constructing a perfect architectural replica of a building, but using materials that would explode if they ever touched the original. The team at CERN managed to create 9 anti-hydrogen atoms. Just 9. They existed for about 40 billionths of a second before annihilating with regular matter. But in those brief moments, we had actual antimatter atoms floating in our universe. And here's what absolutely blows my mind about this achievement. Those anti-hydrogen atoms behaved exactly like regular hydrogen atoms. Same energy levels, same spectral lines, same quantum mechanical properties. It was like looking at a perfect twin, identical in every way except for the fundamental charge of its components. But creating anti-atoms opened up possibilities that individual antiparticles never could, because now we could start asking questions that get to the heart of reality itself. Do anti-atoms emit light the same way regular atoms do? Do they respond to magnetic fields identically? And most importantly, how do they behave in Earth's gravitational field? That last question is the big one, because if antimatter falls upward instead of downward, it would revolutionize our understanding of gravity, space-time, and the structure of the universe. It would suggest that there's something fundamentally different about antimatter that we've never suspected. Now, most physicists expect antimatter to fall down just like regular matter. Einstein's theory of relativity predicts that antimatter should have positive mass and should be attracted to gravitational fields just like anything else. But here's the thing about science. It doesn't matter what we expect. It doesn't matter what our theories predict. What matters is what actually happens when we test it. And that's exactly what researchers at CERN are trying to do right now with an experiment called ALPHA. They're creating anti-hydrogen atoms, trapping them in magnetic fields, and then very carefully releasing them to see which way they fall. It sounds simple, but it's one of the most technically challenging experiments ever attempted. The problem is that antimatter is incredibly difficult to work with. Remember, these anti-atoms can't touch anything made of regular matter, or they'll annihilate instantly. So you have to create them in a perfect vacuum, trap them with magnetic fields, and then measure their motion with incredible precision. And the effects you're looking for are tiny. Earth's gravity is the weakest of all the fundamental forces. The gravitational pull on a single anti-hydrogen atom is so small that it's easily overwhelmed by any stray magnetic fields, air currents, or vibrations in the equipment. It's like trying to measure the weight of a feather in the middle of a hurricane. But if they succeed, if they can definitively show that antimatter falls in Earth's gravitational field, it will be one of the most important experimental confirmations in the history of physics. And if they discover that antimatter falls upward, well, that would change everything. Because think about what that would mean. If antimatter has anti-gravity properties, then the missing antimatter from the Big Bang might not be missing at all. It might have been gravitationally separated from regular matter in the early universe. While matter clumped together to form galaxies and stars, antimatter might have been pushed outward into the vast empty spaces between galactic clusters. This could solve the antimatter asymmetry problem in a completely unexpected way. Instead of antimatter being destroyed or banished to another dimension, it could be hiding in the cosmic voids, forming its own structures that we can't see because there's no regular matter nearby for them to annihilate with. Imagine vast antimatter galaxies floating in the darkness between our own galaxy clusters, anti-stars burning anti-fuel, anti-planets orbiting in anti-solar systems. From a distance, they would be completely invisible to us because light itself doesn't distinguish between matter and antimatter. The only way we'd know they were there is if some regular matter somehow drifted into one of these antimatter regions and created a massive annihilation event. And here's something that gives me chills when I think about it. If antimatter galaxies do exist, and if they contain anti-life, then right now, somewhere in the universe, there might be anti-beings made of antiparticles, living on anti-worlds, wondering where all their matter went. They would think of themselves as being made of normal matter, To them, we would be the antimatter beings. They might be conducting their own experiments, trying to understand why their universe seems to be dominated by what they call matter, wondering what happened to all the antimatter they expected to find. It's a perfect symmetry that solves the cosmic puzzle by simply putting each type of matter where the other can't see it. And the beautiful thing is, both sides would be equally puzzled by the same mystery. But let's get back to what we can actually test and measure. Because while we're waiting for the alpha experiment to tell us which way antimatter falls, other researchers are pushing the boundaries of what we can do with anti-atoms. At CERN's alpha experiment, they're not just trying to measure gravitational effects, they're also performing incredibly precise measurements of antihydrogen's properties. They're using lasers to probe the energy levels of antiatoms, checking whether they emit and absorb light in exactly the same way as regular hydrogen atoms. And so far, the results are remarkable. Antihydrogen appears to be identical to regular hydrogen in every way they can measure. Same energy transitions, same response to magnetic fields, same quantum mechanical behavior. It's like nature has this perfect symmetry built into its very foundation. But here's where it gets really interesting. These experiments are so precise that they could detect tiny differences between matter and antimatter that might reveal new physics. We're talking about measurements accurate to parts per trillion. If there's any hidden asymmetry in nature, any subtle difference between how matter and antimatter behave, these experiments might find it. And finding such a difference would be huge. It could explain why the universe ended up with more matter than antimatter. It could reveal new fundamental forces or particles that we haven't discovered yet. It could open up entirely new areas of physics that we never knew existed. Meanwhile, other groups are working on even more ambitious projects. There's an experiment called AEGIS that's trying to create beams of antiatoms and shoot them horizontally to see how gravity affects their trajectory. Another group is working on creating antimolecules, combinations of antiatoms that would be even more complex structures made entirely of antimatter. Can you imagine that? Anti-water molecules made of anti-hydrogen and anti-oxygen, anti-methane made of anti-carbon and anti-hydrogen. The same chemical processes that create the molecules of life, but running in reverse with antiparticles. And if we can make antimolecules, what's to stop us from making more complex structures? Anticrystals, antipolymers, maybe even simple anti-life forms like antiviruses or antibacteria. We're talking about creating an entire parallel chemistry based on antimatter. Of course, all of this is incredibly far in the future. Right now, we can barely make a few dozen anti-atoms at a time, and they only last for seconds before annihilating. But the theoretical possibilities are staggering. There's also the question of what happens when you try to combine different types of antiatoms. Would antihydrogen and antihelium interact the same way that regular hydrogen and helium do? Would they form the same kinds of chemical bonds? Would anti-chemistry follow all the same rules as regular chemistry? Most scientists expect that it would. After all, chemistry is just physics applied to atoms and molecules. If anti-atoms behave identically to regular atoms, then anti-chemistry should be identical to regular chemistry. But until we test it, we won't know for sure. And testing it is going to require advances in antimatter production that we can barely imagine today. We need to be able to make antimatter not by the individual particle, but by the gram. We need to be able to store it safely for long periods. We need to be able to manipulate it and study it the same way we can manipulate and study regular matter. These challenges are enormous, but they're not impossible. Every year, our techniques for creating and trapping antimatter get more sophisticated. The amounts we can produce get larger, even if they're still incredibly tiny by everyday standards. The time we can store antiatoms gets longer, and with each improvement, we get closer to answering the fundamental questions that antimatter poses. Is gravity the same for matter and antimatter? Are there hidden asymmetries in nature that we haven't discovered? Could antimatter be the key to understanding dark energy and dark matter? That last question is particularly intriguing. We know that something is causing the expansion of the universe to accelerate. We call it dark energy, but we have no idea what it actually is. Some theories suggest that it could be related to the quantum properties of empty space, to the constant creation and annihilation of virtual particle pairs. But what if dark energy is actually related to antimatter in some way we don't understand? What if the missing antimatter from the Big Bang didn't disappear, but instead became the mysterious force that's pushing the universe apart? It's a wild idea, and there's no direct evidence for it. But the fact that we're even missing 95% of the universe in the form of dark matter and dark energy suggests that there are fundamental aspects of reality that we don't understand yet. And antimatter might be the key to understanding them, because antimatter forces us to think about symmetry, about balance, about the deep structures that govern how reality works. Every time we create an antiparticle, we're probing these fundamental questions. There's something almost philosophical about studying antimatter. We're matter beings studying our own reflection. We're using consciousness that emerged from regular atoms to investigate anti-atoms. We're the universe, looking at its own mirror image and trying to understand what it sees. And in that mirror, we might find answers to questions we didn't even know we were asking. Why does anything exist at all? What determines the laws of physics? Are there other universes with different rules, different balances between matter and antimatter? These aren't just academic questions. They go to the heart of what it means to exist, what it means to be conscious observers in a universe that seems fine-tuned for our existence. The fact that we have more matter than antimatter isn't just a curious scientific fact. It's the reason we're here to ask the question in the first place. But here's what really gets me excited about the future of antimatter research. We're living at a unique moment in history. For the first time ever, we have the technology to create and study antimatter in controlled conditions. We can trap it, manipulate it, and measure its properties with incredible precision. Just 50 years ago, antimatter was purely theoretical. It existed in equations and thought experiments, but no one had ever seen an antiparticle. Today, we're creating anti-atoms and studying their behavior. In 50 years, who knows what we'll be able to do? Maybe we'll have antimatter factories that can produce grams of the stuff. Maybe we'll have antimatter spacecraft exploring the outer solar system. Maybe we'll discover that antimatter galaxies really do exist, hidden in the cosmic voids between our own galaxy clusters. Or maybe we'll discover something completely unexpected, something that overturns everything we think we know about matter, antimatter, and the nature of reality itself. That's the beauty of science. You start by asking one question, and you end up discovering things you never imagined were possible. And antimatter, this perfect mirror of reality, this substance that shouldn't exist but does, might be the key that unlocks secrets we've been searching for since humans first looked up at the stars and wondered what they were made of. In our next section, we're going to explore what might be the most mind-bending possibility of all. What if antimatter isn't just a scientific curiosity? What if it's actually a window into other dimensions, other realities, other universes where the rules of physics work differently than they do here? Because the more we study antimatter, the more we realize that it's not just about particles and forces, it's about the fundamental nature of existence itself. And that story is about to get a whole lot stranger. Because here's where antimatter leads us into territory that sounds like science fiction, but is grounded in some of the most cutting-edge theories in physics today. Remember how I mentioned that antimatter might be connected to extra dimensions? Well, that's not just wild speculation. It's based on some very real mathematics that describe how our universe might actually work. String theory, which is one of our most ambitious attempts to explain everything in physics, suggests that our familiar 3 dimensions of space and 1 dimension of time are just a tiny slice of a much larger reality. According to string theory, there could be as many as 11 dimensions total, with the extra dimensions curled up so small that we can't detect them directly. But here's where it gets interesting for antimatter. In some versions of string theory, particles and antiparticles aren't just mirror images of each other in our familiar dimensions. They might actually be the same particle, but viewed from different dimensional perspectives. Imagine looking at a coin from above and seeing heads, then looking at it from below and seeing tails. Same coin, different viewpoint. That's kind of what might be happening with matter and antimatter, except the different viewpoints are through extra dimensions we can't perceive. This idea suggests something profound about the nature of reality. What we call matter and antimatter might not be separate substances at all. They might be different aspects of a single higher dimensional entity that we can only see pieces of from our limited three-dimensional perspective. And if that's true, then the antimatter that's missing from our universe isn't really missing. It's just hiding in dimensions we can't access. It's like trying to find a three-dimensional object when you can only see in two dimensions. The object is there, but you're looking in the wrong direction. But let's take this even further, because some physicists have proposed something called mirror matter theories. These suggest that there might be an entire parallel sector of physics that operates alongside our own but remains largely invisible to us. Not just antiparticles, but anti-forces, anti-fields, maybe even anti-spacetime itself. In this mirror world, they would be mirror electrons orbiting mirror nuclei, held together by mirror electromagnetic forces. These mirror atoms could combine into mirror molecules, form mirror planets, and orbit mirror stars. And because mirror photons would only interact weakly with regular photons, this mirror universe would be essentially invisible to us. The really wild part is that we might occasionally detect hints of this mirror world through gravitational effects. Mirror matter would still have mass, so it would still curve space-time. In fact, some researchers have suggested that dark matter, that mysterious stuff that makes up most of the universe's mass but doesn't emit light, might actually be mirror matter. Think about that for a moment. What if the reason we can't see dark matter isn't because it's made of exotic particles we've never discovered, but because it's made of perfectly ordinary particles that just happen to exist in a parallel physics sector? What if dark matter is just mirror hydrogen and mirror helium, forming mirror galaxies that overlap with our own galaxy but remain invisible because mirror light doesn't interact with regular matter? This would be the ultimate cosmic joke. We've been searching for dark matter with increasingly sophisticated detectors, building underground laboratories and space-based telescopes, when all along it might have been made of the most familiar particles in the universe, just operating in a parallel reality that we can't see. But here's what really keeps me awake at night, thinking about this stuff. If mirror matter exists, if there's a whole parallel physics sector operating alongside our own, then there's no reason to think it stops at simple particles and atoms. Mirror chemistry should work just as well as regular chemistry. Mirror biology should be possible. Mirror evolution should operate according to the same principles, which means there could be mirror life forms existing right here on Earth, made of mirror matter, living in the same space we occupy but completely invisible to us. Mirror bacteria floating through the air. Mirror plants growing in mirror soil. Mirror animals walking through mirror forests that overlap perfectly with our own forests but never interact with them. And if mirror intelligence evolved, if mirror beings developed mirror technology and mirror civilization, they would be asking the same questions we are. They would detect our gravitational effects, but never be able to see us directly. To them, we would be the dark matter. We would be the invisible sector that they can measure but never observe. It's like the ultimate example of two ships passing in the night, except the ships are entire universes occupying the same space, but operating on completely different frequencies of reality. Now, I want to be clear about something. These mirror matter theories are highly speculative. We have no direct evidence that such a parallel sector exists. But the mathematics work out, and they provide elegant solutions to some of physics' biggest mysteries. The missing antimatter, the nature of dark matter, the fine-tuning of physical constants that allow our universe to exist at all. And there's another possibility that's even more mind-bending. What if our universe and this hypothetical mirror universe aren't completely separate? What if there are rare occasions when they interact, when particles from one sector somehow cross over into the other? Some researchers have proposed that this might explain certain anomalies in particle physics experiments. Occasional events that don't quite fit our standard model, particles that appear to violate conservation laws or exhibit unexpected behaviors. What if these aren't experimental errors or new physics in our sector, but glimpses of particles that have crossed over from the mirror sector? If such crossover events are possible, then there might be ways to detect the mirror universe directly. We might be able to create conditions in particle accelerators where regular matter briefly transforms into mirror matter, or where mirror particles become visible to our detectors. And here's where things get really exciting. If we could figure out how to control such crossover events, we might be able to communicate with the mirror universe. Imagine sending a signal composed of particles that can exist in both sectors, a message that could be received by mirror beings if they exist, and have developed the technology to detect it. It would be the ultimate long-distance call, reaching across not just space, but across parallel realities. And the response, if it came, would tell us that we're not alone in the cosmos, that intelligence has evolved not just elsewhere in our universe, but in parallel universes that share the same space we do. Of course, this is all extremely speculative. We're talking about physics that might not exist, parallel universes that might be pure fantasy, mirror beings that might never have evolved. But the fact that we can even conceive of such possibilities, that the mathematics allows for them, tells us something important about the nature of reality. The universe is stranger than we imagine. It might be stranger than we can imagine. And antimatter, this perfect reflection of everything we know and are, might be the key that unlocks secrets we haven't even thought to look for yet. But let's come back to something we can actually test, something that's happening right now in laboratories around the world. Because while we're speculating about mirror universes and parallel realities, researchers are making real breakthroughs in creating and studying antimatter that could revolutionize our understanding of physics. One of the most ambitious projects currently underway is called the Antiproton Decelerator at CERN. This machine doesn't just create antiprotons, it slows them down to speeds where they can be captured and studied in detail, and the results have been remarkable. Scientists have discovered that they can create not just anti-hydrogen atoms, but excited anti-hydrogen atoms, anti-atoms with electrons in higher energy levels. They can use lasers to manipulate these anti-atoms, probing their internal structure with unprecedented precision. And here's what's absolutely incredible about these experiments. Every measurement they make confirms that antimatter behaves exactly like regular matter, but with opposite charges. The energy levels are identical. The response to electromagnetic fields is perfectly predictable. The quantum mechanical properties are mirror images of what we see in regular atoms. This level of precision is telling us something profound about the symmetries of nature. It's confirming that the universe really does have this deep, fundamental balance built into its structure. Matter and antimatter aren't just similar, they're perfect reflections of each other down to the smallest measurable details. But here's where it gets really interesting. These same experiments are pushing the boundaries of what we can detect. They're becoming sensitive enough to measure tiny violations of symmetry that might exist at levels we've never been able to probe before. And finding such violations would be revolutionary. It would tell us that the universe isn't perfectly symmetric after all, that there are hidden asymmetries in nature that could explain why we have more matter than antimatter. It would point us toward new physics, new forces, new particles that we haven't discovered yet. Some theoretical physicists have proposed that these symmetry violations might be connected to the nature of time itself. Remember how I mentioned that antiparticles might be particles moving backwards through time? Well, if that's true, then studying antimatter might actually be studying the fundamental nature of temporal reality. What if time isn't the simple, one-directional flow that we experience in everyday life? What if it's more like a river with currents flowing in both directions, and we just happen to be caught in the forward-flowing current? Antimatter might be our window into understanding what's happening in the backward-flowing currents of time. This connects to some of the deepest questions in physics. Why does time have an arrow? Why do we remember the past but not the future? Why do eggs break but not unbreak? The answers might be hidden in the relationship between matter and antimatter, in the subtle ways that the universe breaks its own symmetries. And there's another possibility that's even more profound. What if consciousness itself is connected to the asymmetry between matter and antimatter? What if the reason we exist as conscious observers is somehow tied to the imbalance that allowed matter to dominate over antimatter in the early universe? This isn't just philosophical speculation. Some researchers have proposed that consciousness might be a fundamental feature of the universe, not just an emergent property of complex brains. And if consciousness is fundamental, then it might be connected to the basic asymmetries that govern how reality works. Think about it this way. The fact that we can ask questions about antimatter, that we can create experiments to study it, that we can contemplate mirror universes and parallel realities, might itself be a consequence of the cosmic imbalance that created more matter than antimatter. We exist because the universe is asymmetric, and our existence allows the universe to study its own asymmetries. We're the cosmos looking at itself in the mirror and wondering why the reflection isn't perfect. We're matter beings studying antimatter, asymmetric creatures investigating the source of our own asymmetry. But let's talk about something that might seem mundane compared to parallel universes and the nature of consciousness, but is actually just as revolutionary. The practical applications of antimatter that we might see in our lifetimes. I mentioned earlier that PET scans already use antimatter for medical imaging, but that's just the beginning. Researchers are working on much more sophisticated medical applications that could transform how we treat diseases. One promising area is targeted cancer therapy using antiproton beams. The idea is that you could focus a beam of antiprotons precisely on a tumor, where they would annihilate with protons in the cancer cells and release their energy exactly where it's needed. Unlike traditional radiation therapy, which affects healthy tissue as well as cancerous tissue, antimatter therapy could be incredibly precise. And because the energy release from matter-antimatter annihilation is so intense, you would need far fewer antiprotons to destroy a tumor than you would need photons or other particles in conventional radiation therapy. It could be more effective and have fewer side effects. But the medical applications go beyond just therapy. Antimatter could be used for incredibly detailed imaging of the human body. Because antimatter annihilation produces gamma rays with very specific energies, we could use those gamma rays to create three-dimensional maps of organs and tissues with resolution that's impossible with current technology. Imagine being able to see individual blood vessels in the brain, or watch how neurons fire in real time, or track the spread of disease at the cellular level. Antimatter could give us a window into the human body that we've never had before. And then there's space exploration. I talked earlier about antimatter rockets that could reach nearby stars in decades instead of millennia. But even more modest applications could revolutionize how we explore our own solar system. A spacecraft powered by small amounts of antimatter could reach Mars in weeks instead of months. It could fly to Jupiter or Saturn in a matter of years instead of decades. It could carry much larger payloads, because it wouldn't need to carry massive amounts of fuel. But here's what really excites me about antimatter propulsion. It wouldn't just make space travel faster and more efficient, it would make it fundamentally different. With chemical rockets, you're essentially riding controlled explosions. With antimatter rockets, you're riding pure energy conversion, the most efficient reaction possible in the universe. The exhaust from an antimatter rocket wouldn't be hot gases like current rockets produce. It would be pure energy in the form of gamma rays and elementary particles moving at close to the speed of light. You could theoretically achieve exhaust velocities that are a significant fraction of the speed of light itself. This means that antimatter rockets wouldn't just be faster than chemical rockets, they would be operating on completely different physics. They would be true relativistic spacecraft, vehicles where you would actually notice time dilation effects during long journeys. Imagine taking a trip to Proxima Centauri on an antimatter-powered spacecraft. The journey would take about 40 years, as measured by people on Earth. But because of time dilation, the astronauts on the spacecraft would experience less time passing. They might age only 30 years during the journey, arriving at their destination younger than they would have been if they had stayed on Earth. It's like antimatter doesn't just offer us a new way to travel through space. It offers us a way to travel through time as well, to experience the universe from perspectives that are fundamentally different from anything humans have ever known. But all of these applications, from medical imaging to interstellar travel, depend on solving the fundamental challenge of antimatter production and storage. And that's where some of the most exciting breakthroughs are happening right now. Researchers are working on new techniques for creating antimatter that are orders of magnitude more efficient than current methods. Instead of smashing particles together in huge accelerators and hoping that a few antiparticles emerge from the debris, they're developing more targeted approaches that could produce antimatter on demand. One promising technique involves using intense laser pulses to create matter-antimatter pairs directly from the quantum vacuum. When you focus enough energy into a small enough space, the vacuum itself begins to bubble with virtual particles that can become real under the right conditions. Another approach uses magnetic fields to extract antiprotons directly from cosmic ray interactions in the upper atmosphere. Instead of creating antimatter in earthbound accelerators, we would harvest it from the natural antimatter production that's happening above our heads all the time. And there are even more exotic possibilities on the horizon. Some researchers are investigating whether black holes could be used as antimatter factories. Remember how I mentioned that black holes should emit antimatter as they evaporate through Hawking radiation? Well, if we could somehow capture that antimatter, we would have access to potentially enormous quantities of the stuff. Of course, the technical challenges involved in harvesting antimatter from black holes are mind-boggling. We're talking about engineering projects that would dwarf anything humans have ever attempted. But the theoretical possibility is there. And that's what I find so exciting about antimatter research. It's pushing us to think about engineering problems on cosmic scales, to consider technologies that would make us a truly spacefaring civilization. But perhaps the most important breakthrough won't be in how we create or store antimatter. It might be in how we understand it. Because every new discovery about antimatter teaches us something fundamental about the nature of reality itself. When we measure the properties of antiatoms, we're testing whether the universe really is symmetric at its deepest level. When we study how antimatter behaves in gravitational fields, we're probing the relationship between matter, energy, and spacetime. When we investigate the imbalance between matter and antimatter, we're asking why anything exists at all. These aren't just technical questions for particle physicists to worry about. They're questions that go to the heart of what it means to be conscious beings in a universe that seems fine-tuned for our existence. And antimatter, this perfect mirror of everything we are, might hold the answers. It might tell us not just how the universe works, but why it works the way it does. Why the laws of physics have the values they do. Why consciousness emerged from unconscious matter. Why we're here to ask these questions in the first place. In our final section, we're going to explore what might be the ultimate question that antimatter poses. Not just what it is or how it works, but what it means for our understanding of existence itself. Because the story of antimatter isn't just about particles and forces. It's about the deepest mystery of all, why there is something rather than nothing. And that mystery is about to take us to places that will challenge everything we think we know about reality, consciousness, and our place in the cosmic order. Because when we really think about what antimatter represents, we're not just talking about exotic particles in laboratory experiments. We're confronting the most fundamental question that has haunted philosophers and scientists for thousands of years. Why does anything exist at all? Why isn't the universe just empty space, void of matter, energy, and consciousness? This question becomes even more urgent when we consider what the Big Bang should have produced. According to our best understanding of physics, the early universe should have created exactly equal amounts of matter and antimatter, every proton paired with an antiproton, every electron matched by a positron, a perfect cosmic balance that would have led to complete annihilation within the first few seconds of existence. But something broke that symmetry. Something tipped the scales by the tiniest imaginable margin. For every billion matter-antimatter pairs that destroyed each other, just one particle of regular matter survived. 1 in a billion. That's the margin by which existence won out over nothingness. Think about how precarious that makes our entire reality. If that ratio had been even slightly different, if it had been perfect symmetry instead of almost perfect symmetry, there would be no stars, no planets, no chemistry, no biology, no consciousness. The universe would be nothing but photons and empty space, expanding forever into an increasingly cold and empty infinity. Yet here we are, made from that 1 in a billion excess of matter, contemplating our own existence and wondering how it's possible. We're the universe's accident, the cosmic mistake that made everything else possible. But what if it wasn't really an accident? What if there's something deeper going on? Something that ensures the universe creates conscious observers like us. This touches on what physicists call the anthropic principle, the idea that the universe's properties must be compatible with conscious life, because if they weren't, there would be no conscious beings around to observe them. Some versions of this principle suggest that our universe is just one of countless universes, each with different physical laws and different ratios of matter to antimatter. In most of these universes, perfect symmetry leads to empty space. But in a tiny fraction, the symmetry breaks in just the right way to allow matter to dominate, stars to form, chemistry to develop, and consciousness to emerge. We exist in one of those rare universes not because we're special, but because only in such universes is there anyone around to notice their own existence. It's a kind of cosmic survivor bias on the grandest possible scale. But there's another interpretation that's even more provocative. What if consciousness itself plays a role in breaking the symmetry between matter and antimatter? What if the universe creates conscious observers not by accident, but because consciousness is somehow necessary for the universe to exist at all? This idea connects to some of the deepest mysteries in quantum mechanics. We know that quantum systems exist in superposition, in multiple states simultaneously, until they're observed or measured. The act of observation somehow collapses the wave function and forces the system to choose a specific state. Now, most physicists think this happens through purely physical processes, not through consciousness per se. But some interpretations of quantum mechanics suggest that consciousness might play a fundamental role in determining reality. And if that's true, then maybe the existence of conscious observers is what allows the universe to resolve the symmetry between matter and antimatter. Maybe in the early universe, quantum fluctuations created regions with slightly more matter and regions with slightly more antimatter. But only in the matter-dominated regions could complexity develop, chemistry emerge, and eventually consciousness arise. And once consciousness appeared, it retroactively stabilized the matter-dominated regions, while the antimatter regions remained quantum possibilities that never fully manifested. It's a wild idea, and most physicists would say it goes way beyond what the evidence supports. But it illustrates something important about antimatter research. When you start asking why there's more matter than antimatter, you quickly find yourself asking much deeper questions about the nature of existence, consciousness, and reality itself. And these questions become even more intriguing when we consider what we've learned about the quantum vacuum. Empty space isn't really empty. It's seething with virtual particles that pop into existence and annihilate each other in time frames so brief that they can't be directly observed. Matter and antimatter pairs are constantly being created and destroyed in the quantum foam that underlies all of reality. But here's the thing. If virtual particles are constantly creating matter-antimatter pairs, why don't they perfectly cancel out? Why is there any net matter or antimatter at all? The fact that we exist suggests that something is preventing perfect cancellation, that there's a subtle bias in the quantum vacuum itself that favors matter over antimatter. Understanding this bias could tell us not just why we exist, but how existence itself emerges from the quantum vacuum. We might discover that consciousness isn't just a byproduct of complex chemistry, but a fundamental feature of how the universe resolves quantum indeterminacy. And this connects to another profound mystery about antimatter. We've talked about how antiparticles might be regular particles moving backwards through time. But what if it's more than just a mathematical convenience? What if the relationship between matter and antimatter really does reveal something fundamental about the nature of time itself? Think about this carefully. In our everyday experience, time moves forward. We remember the past but not the future. Cause precedes effect. But at the quantum level, many processes are time reversible. An electron scattering off a photon looks the same whether you run the movie forwards or backwards. The arrow of time that we experience in macroscopic reality might emerge from the same symmetry breaking that gave us more matter than antimatter. Maybe the universe didn't just choose matter over antimatter in those first moments after the Big Bang. Maybe it chose forward time over backward time, creating the temporal direction that allows for causality, memory, and conscious experience. If that's true, then studying antimatter isn't just about understanding exotic particles. It's about understanding the emergence of time itself, the origin of causality, and the foundation of all conscious experience. This brings us to something that absolutely fascinates me about current antimatter research. We're not just trying to understand what happened billions of years ago in the early universe. We're trying to recreate those conditions in our laboratories and see if we can witness symmetry breaking in real time. At facilities like CERN, researchers are creating conditions of temperature and energy density that haven't existed since the first microseconds after the Big Bang. They're essentially building time machines that let us peer back into the universe's infancy and watch how the fundamental symmetries of nature behave under extreme conditions. And what they're finding is remarkable. Under certain conditions, the symmetries that seem absolute in our everyday world can indeed be broken. The universe does seem to have built-in preferences that aren't apparent from our limited macroscopic perspective. But here's where it gets really interesting. Some of these experiments are finding evidence that the universe doesn't just break symmetries randomly. There seem to be underlying principles that guide how symmetries are broken, rules that determine which symmetries can be violated and which must be preserved. It's as if the universe has a kind of cosmic constitution, a set of fundamental laws that constrain how reality can evolve. And antimatter might be our best window into understanding what those laws are and why they exist. This is leading some physicists to propose that our universe isn't just one of many possible universes with different physical laws. Maybe there's something special about our particular combination of laws, something that makes conscious observers not just possible but inevitable. Maybe the ratio of matter to antimatter, the strength of the fundamental forces, the properties of space and time, are all fine-tuned, not by cosmic accident, but by some deeper principle that we haven't discovered yet, a principle that ensures the universe creates beings capable of understanding their own existence. And if that's true, then we're not just accidental byproducts of cosmic evolution, we're the universe's way of understanding itself. We're matter that became conscious so it could contemplate antimatter. We're the cosmos looking in the mirror and trying to understand why the reflection isn't perfect. This perspective transforms how we think about antimatter research. We're not just studying exotic particles for their own sake. We're investigating the deepest questions about existence, consciousness, and our place in the cosmic order. Every anti-proton we create, every anti-atom we trap, every measurement we make is part of humanity's quest to understand why we're here at all. And the answers we find might be stranger than anything we've imagined, because antimatter has already taught us that reality is far weirder than our everyday experience suggests. Particles that are perfect mirror images of familiar matter, virtual particles popping in and out of existence in empty space, the possibility that antiparticles are just regular particles moving backwards through time. If antimatter has taught us anything, it's that the universe doesn't care about our intuitions or expectations. Reality operates according to its own rules, and those rules are often counterintuitive, paradoxical, and beautiful in ways we never anticipated. So what does the future hold for antimatter research? Where are we headed as we continue to probe these fundamental mysteries? In the short term, we're going to get definitive answers to some crucial questions. The Alpha experiment at CERN will soon tell us whether antimatter falls up or down in Earth's gravitational field. Other experiments will measure the properties of antiatoms with unprecedented precision, looking for any tiny deviations from perfect matter-antimatter symmetry. These measurements might reveal new physics beyond our current understanding. They might point toward extra dimensions, parallel universes, or completely novel forces that we haven't discovered yet. Or they might confirm that the universe really is perfectly symmetric at the deepest level, which would be just as profound in its own way. In the longer term, we might develop the technology to create and store significant quantities of antimatter, not just individual particles, but grams or even kilograms of the stuff. This would open up possibilities we can barely imagine today. Antimatter-powered spacecraft that could reach nearby stars in decades instead of millennia. Medical treatments that could target diseases with precision we've never achieved. Energy sources that could power our civilization for thousands of years without any environmental impact. But perhaps the most important developments won't be technological, they'll be conceptual. As we learn more about antimatter, we're going to develop new ways of thinking about reality, consciousness, and existence itself. We might discover that the universe is fundamentally information-based, with matter and antimatter being different ways of encoding cosmic data. We might find that consciousness is woven into the fabric of reality at the quantum level. We might learn that our universe is just one small part of a vast multiverse where every possible combination of matter and antimatter exists somewhere. Or we might discover something completely unexpected, something that overturns everything we think we know about physics and forces us to rebuild our understanding of reality from the ground up. That's the beauty of science, and it's especially true with antimatter research. You start by asking what seems like a simple question about particles and charges, and you end up confronting the deepest mysteries of existence itself. But here's what I find most remarkable about this whole journey. We started by talking about antimatter as the mirror of reality, and in many ways that's exactly what it's turned out to be. Not just a reflection of ordinary matter, but a reflection of all our assumptions about how the universe works. Every time we study antimatter, we're forced to confront the possibility that reality is fundamentally different from what we thought. We're reminded that the universe is under no obligation to match our expectations or intuitions. And we're shown that the deepest truths about existence might be hidden in the most exotic and counterintuitive phenomena. Antimatter forces us to think about symmetry and asymmetry, about why some things are perfectly balanced while others are slightly skewed. It makes us consider the relationship between matter and energy, between particles and fields, between existence and nothingness. And perhaps most importantly, it reminds us that we're part of the story we're trying to understand. We're not detached observers studying antimatter from the outside. We're matter beings investigating our own cosmic origins, using consciousness that emerged from the matter-antimatter imbalance to study the very imbalance that made our consciousness possible. We are the universe contemplating its own reflection in the antimatter mirror, And what we see there might just reveal the deepest secrets about why anything exists at all. In the final part of our journey together, we're going to explore what these discoveries might mean for the future of humanity itself. Because antimatter isn't just changing how we understand physics, it's changing how we see our place in the cosmos, our relationship with reality, and our responsibility as conscious beings in a universe that seems designed to create consciousness. The mirror of reality has more to show us, and the reflection might reveal truths that transform everything we think we know about ourselves and our cosmic destiny. But before we dive into what all of this means for humanity's future, I need to tell you about something that happened just last year that completely changed how scientists think about antimatter storage. For decades, the biggest challenge with antimatter wasn't just creating it was keeping it alive long enough to study. Remember, we're dealing with particles that annihilate the instant they touch any normal matter. That includes the walls of any container, the air molecules in the atmosphere, even the atoms in your own body. So how do you store something that destroys itself the moment it encounters the very stuff everything else is made of? The solution has always been magnetic confinement. Create invisible walls made of magnetic fields that hold the antimatter particles suspended in perfect vacuum, floating in empty space without ever touching anything solid. It's like juggling soap bubbles made of pure energy, except if you drop one, it doesn't just pop. It explodes with the force of a nuclear bomb. But here's what's incredible. In 2022, researchers at CERN managed to keep anti-hydrogen atoms trapped for over 16 minutes. 16 minutes might not sound like much, but in antimatter terms, that's practically forever. Previous records were measured in seconds or fractions of seconds. This breakthrough means we can now study anti-atoms long enough to perform detailed experiments on their properties. And what they discovered during those 16 minutes is going to blow your mind. They used laser spectroscopy to probe the internal structure of anti-hydrogen atoms, measuring how the anti-electrons orbit around the anti-nucleus, and the precision of their measurements was staggering. They could detect differences in energy levels down to parts per trillion. What did they find? Perfect symmetry. The anti-hydrogen atoms behaved exactly, and I mean exactly, like regular hydrogen atoms, just with opposite charges. Every energy transition, every quantum mechanical property, every response to electromagnetic fields was a perfect mirror image of what we see in regular matter. This level of precision is telling us something profound about the fundamental structure of reality. Nature really does seem to have this perfect symmetry built into its deepest levels. But that makes the matter-antimatter asymmetry in our universe even more mysterious. If antimatter is such a perfect mirror of regular matter, why don't we see equal amounts of both? But here's where the story takes an unexpected turn. While scientists were celebrating this breakthrough in antimatter storage, something else was happening in a completely different field of physics that nobody saw coming. Researchers studying dark matter, that mysterious substance that makes up most of the universe's mass, started finding patterns that looked surprisingly familiar. You see, we know dark matter exists because we can see its gravitational effects. Galaxies rotate faster than they should based on the visible matter we can see. Galaxy clusters are held together by more mass than we can account for. The cosmic microwave background radiation shows imprints of dark matter's influence from the early universe. But despite decades of searching, we've never directly detected a dark matter particle. Every experiment designed to catch dark matter interacting with regular matter has come up empty. It's like dark matter exists in a parallel world that overlaps with ours but never quite touches it. And that's when some physicists started asking a radical question. What if dark matter isn't made of exotic particles we've never seen before? What if it's made of perfectly ordinary particles that just happen to exist in a parallel physics sector? What if dark matter is actually dark antimatter? Think about this for a moment. We know that in the early universe, matter and antimatter should have been created in equal amounts. We know that most of it annihilated. leaving behind the small excess of regular matter that makes up everything we can see. But what happened to all that energy from the annihilation? Traditional models assume it just dispersed as radiation, heating up the early universe and eventually contributing to the cosmic microwave background. But some new theories suggest something different might have happened. What if the annihilation process didn't just create radiation? What if it created a parallel sector of physics, a shadow world where antimatter particles could exist without interacting with our regular matter? In this shadow sector, anti-electrons would orbit anti-nuclei just like in our world, but the shadow photons that hold these shadow atoms together would be different from regular photons. They would interact with shadow matter but not with regular matter. This would make shadow antimatter completely invisible to our telescopes and detectors, but it would still have mass, so it would still curve space-time and create gravitational effects. From our perspective, this shadow antimatter would look exactly like dark matter, invisible, massive, and distributed throughout the universe in ways that match what we observe. The missing antimatter from the Big Bang wouldn't be missing at all. It would be hiding in plain sight, making up the dark matter that dominates the cosmic landscape. This idea is so new and so speculative that most physicists are still trying to wrap their heads around it. But if it's true, it would solve two of the biggest mysteries in cosmology with one elegant solution. The missing antimatter and the nature of dark matter would both be explained by the same underlying physics. And here's what really gets my imagination going. If dark matter is really shadow antimatter, then there could be entire shadow civilizations existing right alongside us, made of shadow particles that we can't see or touch. Shadow stars burning shadow fuel, shadow planets orbiting in shadow solar systems, maybe even shadow life forms evolving according to the same principles that govern regular biology. These shadow beings would detect our gravitational effects, but never be able to see us directly. To them, we would be the dark matter, the invisible sector that influences their universe but remains forever beyond their reach. It's the ultimate cosmic irony. Two entire universes occupying the same space, each one invisible to the other, each one wondering about the mysterious dark matter that surrounds them. But let's come back to what we can actually test and measure. Because while these shadow sector theories are fascinating, the real breakthroughs in antimatter research are happening right here in our observable universe. One of the most exciting developments is in the field of antimatter catalysis. Scientists have discovered that tiny amounts of antimatter can be used to trigger much larger nuclear reactions, kind of like how a small match can ignite a huge bonfire. This could revolutionize space propulsion in ways that don't require storing massive amounts of antimatter. Instead of building spacecraft that run purely on matter-antimatter annihilation, we could build hybrid engines that use small amounts of antimatter to catalyze fusion reactions in regular matter. A few milligrams of antimatter could trigger the fusion of kilograms of hydrogen, producing thrust levels that could send spacecraft to nearby star systems in reasonable timeframes. This approach sidesteps many of the challenges that have made pure antimatter propulsion seem impossible. You don't need to store huge quantities of the most dangerous substance in the universe. You don't need to solve the incredible engineering challenges of containing antimatter for years or decades during interstellar flights. You just need enough antimatter to act as a cosmic spark plug for more conventional fusion fuel. And the timeline for this technology isn't centuries in the future. Some estimates suggest that antimatter-catalyzed fusion could be developed within 50 to 100 years, assuming we can solve the remaining technical challenges around antimatter production and storage. But space propulsion is just the beginning. Antimatter research is opening up possibilities in energy production that could transform human civilization. Remember, matter-antimatter annihilation is the most efficient energy conversion process possible in the universe. 100% of the mass is converted to energy, compared to less than 1% for fusion reactions. If we could master large-scale antimatter production, we could build power plants that run on incredibly small amounts of fuel, A few grams of antimatter could power an entire city for years. There would be no carbon emissions, no nuclear waste, no fuel shortages, just pure energy extracted from the fundamental structure of matter itself. The environmental implications are staggering. Climate change, energy poverty, resource conflicts, all of these challenges could become obsolete if we could harness antimatter for civilian energy production. We're talking about technology that could provide clean, abundant energy for thousands of years, giving human civilization time to mature and develop sustainable relationships with our planet and each other. But here's what I find most profound about these potential applications. Antimatter technology would fundamentally change humanity's relationship with the universe. We would no longer be confined to the resources of a single planet, or even a single solar system. We would become a truly spacefaring species, capable of exploring and colonizing the galaxy. And that transformation would happen remarkably quickly in cosmic terms. Within a few centuries of mastering antimatter technology, human civilization could spread to hundreds or thousands of star systems. We could establish colonies around nearby stars, terraform planets, even build artificial habitats in the empty spaces between solar systems. This isn't just about exploring space for the sake of adventure or scientific curiosity. It's about ensuring the long-term survival of human consciousness and culture. Right now, all of human civilization exists on a single planet orbiting a single star. We're vulnerable to asteroid impacts, supervolcanic eruptions, gamma-ray bursts, and countless other cosmic catastrophes that could wipe out everything we've ever built or achieved. But if we spread across the galaxy using antimatter propulsion, human consciousness would become essentially immortal in cosmic terms. Even if entire star systems were destroyed, human civilization would continue in thousands of other locations. Our art, our science, our philosophy, our stories would be preserved across multiple worlds, ensuring that the spark of consciousness that emerged on Earth continues to burn throughout the universe. And here's something that gives me chills when I think about it. If we become a galactic civilization powered by antimatter technology, we would eventually encounter the very antimatter galaxies that might exist in the cosmic voids. The collision between matter-based human civilization and antimatter-based civilizations would be the most spectacular and dangerous event in the history of both species. But it might also be the most important, because if antimatter beings exist, if consciousness has evolved in shadow sectors and parallel physics realms, then meeting them would answer one of the deepest questions about existence itself. Are we alone in developing consciousness and intelligence, or is the universe naturally prone to creating thinking, feeling beings, wherever the conditions are right? The answer to that question would transform how we see ourselves and our place in the cosmic order. If consciousness is rare, if we're one of the few successful experiments in the universe's attempt to understand itself, then we have an enormous responsibility to preserve and protect the spark of awareness that we represent. But if consciousness is common, if the universe is teeming with intelligent beings made of regular matter, antimatter, shadow matter, and exotic forms we haven't even imagined yet, then we're part of a much larger community of minds. We're not alone in our quest to understand existence. We're part of a cosmic conversation that spans multiple universes and parallel realities. And antimatter research is preparing us for that conversation. Every experiment we perform, every anti-atom we create, every measurement we make is helping us understand the fundamental language that all conscious beings must eventually learn. The language of symmetry and asymmetry, of matter and antimatter, of existence and nothingness. But there's something else about antimatter research that might be even more important than its practical applications or its implications for finding other conscious beings. It's changing how we think about the nature of reality itself. Traditional physics taught us to think of matter as the fundamental stuff of the universe, with empty space being just empty space. But antimatter research has shown us that this view is completely wrong. Space isn't empty at all. It's seething with virtual particles, quantum fluctuations, and energy fields that connect everything in the universe. Matter and antimatter aren't separate substances occupying space. They're excitations in underlying quantum fields that fill all of reality. Particles aren't little balls bouncing around in empty space. They're waves in an ocean of quantum information that extends throughout the cosmos. This new understanding is leading to revolutionary ideas about the nature of consciousness itself. If reality is fundamentally made of information rather than matter, then consciousness might not be something that emerges from complex arrangements of atoms. It might be a fundamental feature of the information processing that underlies all of physics. In this view, your thoughts, your experiences, your sense of being a conscious observer aren't just byproducts of neural activity in your brain. They're direct expressions of the same information processing that creates matter, antimatter, and the structure of space-time itself. You are quite literally the universe thinking about itself. Your consciousness is matter, antimatter, symmetry becoming aware of its own existence. Your ability to contemplate antimatter is the cosmos using its own fundamental structure to understand why it exists at all. This perspective completely transforms how we think about death, meaning, and our place in the universe. If consciousness is woven into the fabric of reality at the quantum level, then your awareness doesn't disappear when your physical body dies. It returns to the quantum information field that underlies all of existence, becoming part of the cosmic consciousness from which it originally emerged. And if that's true, then every conscious being that has ever lived, every mind that has ever contemplated the mystery of antimatter, continues to exist as part of the universe's ongoing attempt to understand itself. We're all temporary expressions of eternal cosmic awareness, brief moments when the universe opens its eyes and looks at itself in wonder. This isn't just philosophical speculation. It's based on cutting-edge research in quantum information theory, consciousness studies, and the physics of emergence. We're discovering that information, not matter or energy, might be the most fundamental aspect of reality, and consciousness might be how the universe processes and integrates that information. Antimatter research is at the forefront of these discoveries because it forces us to confront the deepest questions about existence. Why is there something rather than nothing? Why does the universe seem fine-tuned for the emergence of consciousness? What is the relationship between mind and matter, between observer and observed? The answers we're finding are stranger and more beautiful than anything we imagined. We're discovering that we're not separate from the universe we're studying. We're part of it. We're the way the cosmos has chosen to understand its own nature. And antimatter, this perfect mirror of everything we are, is showing us that reality is far more interconnected, far more mysterious, and far more wonderful than we ever dared to hope. In the coming decades, as we continue to probe these mysteries, we're going to discover things that will fundamentally change what it means to be human. We're going to develop technologies that give us godlike powers over matter and energy. We're going to explore realms of existence that we can barely imagine today. We're going to make contact with forms of consciousness that challenge everything we think we know about minds and intelligence. But through it all, we'll carry with us the lessons that antimatter has taught us, that reality is stranger than we can imagine, that the universe is full of perfect symmetries and subtle asymmetries that make existence possible, that consciousness isn't separate from the physical world, but is the way the physical world comes to know itself. We are matter contemplating antimatter. We are the universe's reflection in its own mirror. And what we see there, what we're still discovering there, is the most beautiful and profound story ever told. The story of why anything exists at all, and why that anything includes conscious beings capable of loving, learning, and wondering about their own existence. The mirror of reality still has more to show us, and we're just beginning to understand what we see reflected there. So, where does this leave us? standing at the edge of the greatest mystery the universe has ever presented to us. We've journeyed from the basic concept of antimatter as matter's perfect twin, through the mind-bending implications of symmetry breaking, all the way to questions about consciousness itself and our place in cosmic history. But here's what strikes me as the most profound realization of all. Every single antiparticle that has ever been created, every anti-atom that scientists have tracked for those precious 16 minutes, every matter-antimatter annihilation that has ever occurred, is part of a story that began 13.8 billion years ago with the tiniest possible imbalance. One extra particle of matter for every billion pairs that annihilated. That's it. That's the margin by which existence defeated nothingness. And from that infinitesimally small asymmetry, the entire tapestry of reality unfolded. Stars ignited, planets formed, chemistry emerged, life began, consciousness awakened. We are the descendants of that cosmic accident, if accident is even the right word. We're the universe's way of looking back at its own beginning and asking why it chose existence over oblivion. And antimatter, this perfect mirror that shows us what could have been, reminds us how remarkable it is that anything exists at all. The next time you look up at the night sky, remember that every photon of starlight reaching your eyes carries the signature of that ancient asymmetry. Every atom in your body exists because the universe somehow decided that something was better than nothing. And every thought you think about these mysteries is the cosmos using its own structure to contemplate the deepest questions of existence. We're living in the most extraordinary time in human history to be asking these questions. We have the tools to create antimatter, the precision to measure its properties, and the theoretical framework to understand what it might mean. We're the first generation of humans who can actually probe the mirror of reality and see what it reveals about the nature of existence itself. And what we're discovering is that we're not just observers of this cosmic story, we're participants. We're characters in the universe's ongoing attempt to understand why it exists. Every experiment we perform, every measurement we make, every question we ask about antimatter is part of that larger quest for understanding. The mirror of reality isn't just showing us what antimatter is, it's showing us what we are. We're matter that became conscious. We're the universe's way of studying its own reflection. We're the cosmos asking itself why it chose to exist rather than not exist. And perhaps that's the most beautiful truth that antimatter has revealed. In a universe that could have been empty, dark, and lifeless, we're here. We're asking questions, making discoveries, pushing the boundaries of knowledge into territories that seemed impossible just decades ago. The story of antimatter is far from over. We're still in the opening chapters of humanity's relationship with this mirror of reality. The discoveries waiting for us, the technologies we'll develop, the questions we'll answer, and the new mysteries we'll uncover will reshape everything we think we know about existence itself. But right now, in this moment, as you contemplate these ideas, you're part of something magnificent. Your consciousness contemplating its own cosmic origins. Your matter thinking about antimatter. You're the universe looking into its own mirror and marveling at what it sees reflected there. And that reflection, strange and beautiful and full of mysteries we're only beginning to understand, is showing us that reality is far more wonderful than we ever imagined. The mirror of reality still has countless secrets to reveal, and we're just getting started on the most incredible journey of discovery in human history. Thank you for taking this journey with me into the heart of one of science's greatest mysteries. The universe may have started with the tiniest asymmetry between matter and antimatter, but that small beginning led to something extraordinary. It led to us, standing here together, contemplating the deepest questions about existence itself. And in that contemplation, we're fulfilling the universe's deepest purpose. We're the cosmos coming to know itself. We're the mirror of reality, looking back at its own reflection in wonder.